Our world is driven by electricity. It's all around us. Most of us wouldn't know how to survive without it. The phones in our pockets and the computers that you're watching this on all run on electricity. I've been studying circuits for a few years now, and I feel pretty confident I can show you guys a couple things. It's important that we learn this so we know a little bit of the calculations that will come up at some point in your life. We're going to go over, first of all, Ohm's law, and then Kirchhoff's current law, Kirchhoff's voltage law, and then finally we'll go over a couple safety tips. Let's start with Ohm's law. But before we get into that, we need to know a couple important terms. I found these on symbols and prefixes on the IEEE-PES.org website. First of all, we have voltage, which is represented with a V, and it's in the unit volts. Then we have current, which uses the symbol I, and it's the unit amperes. We have resistance, and this unit, right here is called an ohm, and then the unit's ohms. And then we have power, which is represented with the W, and that is in the unit watts. So now that we know a couple of the terms, we can talk about Ohm's formula. Ohm's law's formula is V equals I times R. So voltage equals current times resistance. You can manipulate these and get these ones by dividing out. So you have current equals volts times resistance, and then resistance equals volts times, or over current. And then this here is the power formula. Power equals volts times current. This is what you would probably see on your electronics. It would give you a wattage. So now we can look at Kirchhoff's current law. Kirchhoff's current law talks about a node. The node here is in between two resistors. Every node has to be in between components. So you have a voltage source and two resistors represented by these squiggly lines. So we have a node here, and a node here. So if we're going to use the current law, which says that all current that enters a node must leave a node. So it's easier to just sum it leaving the node and make it equal to 0 to make the calculations a lot easier. So we're going to go VA minus 3 divided by 1. So this right here is the formula for current, V divided by R. And we'll have VA minus 0, this is the ground, divided by 2 equals 0. We'll solve it out, multiply both sides, multiply it all by 2, and then bring over the negative 6. And when we solve it, we'll get VA equals 2 volts. So what it's saying is that there's 2 volts at this node. So what's happening here is, as you're coming across here, the 1 ohm resistor is consuming 1 volt of power, and then the 2 ohm resistor is consuming 2 volts. And then you have 0 volts at the 0 ground. Now we can look at Kirchhoff's current law. We'll use the same diagram for the current law. Let's take a break and show the audience. Back to Kirchhoff's current law. The current law states that in a mesh, which is any square contained by wires, that the current going around the mesh must sum to 0, or the voltages of each component rather. You represent it with the current throughout the mesh. So with the current law, we're going to go a rise on the source, because it goes from negative to positive, so that's a rise. So there's a 3. And then a drop on a resistor. Resistors always are represented by a drop. So here we'll go IA, which is the current in the mesh, times the 1 ohm resistor, which we're getting right here, volts equals I times R. So we have R times I. And that's a negative because it's a drop. Then we have minus I2, or IA times 2, and then sum it all to 0. So then we'll solve this out, and we'll get 3 equals 3 times IA, divided by 3, we'll have IA equals 1. So what this is saying is that there's 1 amp of current going through this entire circuit. Unlike with the voltage, it will not drop. The current stays, it comes out of the source, and it has to come back into the source. The ground is irrelevant for that. Now let's discuss some safety tips that are very important when it comes to dealing with electricity. We've all probably heard about a child sticking a fork into an outlet and getting electrocuted. Well, the reason that happens is if you were to take a fork and put it in the outlet, a circuit is created. So the electricity comes out of it, goes through the fork, and then through your hand, through one part of your finger and out the other, making a closed circuit. That electrocutes your hand, but doesn't hurt you very bad. Now, it could be a lot worse. If you were to, say, be in the kitchen and you were to put something in a socket with one hand and then had your other hand on the faucet, you would close a circuit that would go down one arm, across your heart, and then into the other arm, into the metal faucet. This would probably kill you. So it's very important that when dealing with electricity, you always put your opposite hand behind your back when you're touching any electrical components that could electrocute you. So not only with a fork, because most people aren't putting a fork in the wall, but dealing with any electricity, always put a hand behind your back. That will definitely save you one day. In conclusion, we went over Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, and a little bit of safety tips. Hope you guys learned something from this. It's very basic. It gets way more complicated, a lot of calculus-based stuff, but this is the basics of it, and most people only need to know about this much. Thank you guys.